Okay, here we are filming the answer key. This is actually a second attempt. I started off and immediately said something stupid, so I'm starting over. But the idea here is that if we're trying to find the area under a curve, that's what our integral notation is telling us to do. From 0, this is 0 to 10. Really, when we're asked to find the area with 5 rectangles, left-hand endpoints is critical. So I divide this into fifths for my 5 rectangles. That's every 2 squares. On the left-hand side, I get an endpoint there. That's 3 units up, 2 units wide, so it's going to be 3 by 2. This one looks like it's about 4 up and 2 wide, of course. This one looks like it's about 7 up and 2 wide, 7 by 2. The fourth rectangle looks like it's about 7.5 by 2. And the last one is also about 7 by 2. So some is over counting out here, but then there's under counting of the area right there. As you would make these mathematically narrower and narrower, you'd become more and more accurate. But this is just to get you thinking about how we do this process mathematically. 14, 15, and 14. And we add those up, and what is that? 28, 38, 43, 51, 57, I'm hoping. Check my math. And that would be the approximate area there. Okay, so find the area under the curve now. We've got an equation, all right, and the interval is from 0 to 3. Okay, 6 rectangles will mean they're every half unit now, not every 2, even though it's 2 squares. That's 1, that's 2, that's 3. If I plug in 0 right here, I get 3. So let's see, let's call that 1. Well, let's go out to the end and see how high it is so we can adjust our scale more sensibly. Plug in 3, and I'll get 9 minus 6 plus 3. So that's only up to 6. So if I go right there is 1, 2, 3, 4, there's 5, and there's 6. I know that when I'm out here at 3, I'll be up there. When I start at 0, it's at 3. When I go to 1, it's 1 minus 2 plus 3. So that's down to 2 right there. And then when I'm at 2, that's 4 minus 4 plus 3. I'm back up to 3. Okay, so it's, as you know, a quadratic, so it's going to be a parabola, and it's going to go something like this. All right? And then we're going to divide it into our 6 rectangles, just like before. And it says right-hand endpoints now. Okay, so I'm going to draw these vertical lines, and the thing is I've already evaluated for the whole numbers. If I go to 0.5, should be a little bit more systematic about this, make a little chart, I guess. That would be really a good thing to do. Be organized. There's our x, there's our f of x, and I'm going to use these 6 values. Okay.
So 0, we've already got that as 3. 0.5, when I square 0.5, I get 1/4. I'm just going to cheat over here. And then 0.5 is going to be, when I multiply by 2 minus 1 plus 3. So that's going to be negative 3/4 plus 3 will be 2.25. That's f of 0.5 then. 2.25. When I plug in 1, I get 2. When I plug in 1.5, right there, that's going to give me 2.25 when I square it. Minus 3 plus 3 is going to give me also 2.25. Should know that from symmetry. 2, I get 3 also from symmetry. And then 2.5, plug that in. 2.5 squared is 6.25. Minus 5 plus 3 is going to give me 4.25. And then finally 3 is going to give me 6.
Alright, so I have these values, and what I'm going to do is multiply each one of them by how wide it is. Okay, and I'm going to start over here because it's a right-hand endpoint. I'm going to draw a cross over, and my first rectangle then will be starting with this value of 2.25. Okay, and I'm going to have my 6 rectangles then go down there. Each one of these will be multiplied by 1/2. Okay, so 2.25 then multiplied by 0.5 will be 1.125, and then multiplied 2, the height right here of exactly 2, let's see, right there is 2, multiplied by 1/2 is going to be exactly 1. And then 2.25 again, multiplied by 0.5 will be that. 3 cut in half is going to be that. 4 cut in half is going to be 2.125. And then 6 cut in half is going to be 3. So again, it's just a matter of adding these up. That's 1/8, 2/8, 3/8 plus 0.5. So that's 7/8. I'll just keep it as a fraction. And then that's going to be 5, 6, 7, 8, 9. 9 and 7/8, or what is that going to be? 9.875, I think. All right, would be the approximate area underneath that curve when you add up the right-hand endpoints of all of these rectangles. All right, just to save time, I'm not going to shade them all in, but that would be your 6 different rectangles. All right. Now we're going to check our result using integral calculus. So how would you write this? The integral is going to be from 0 to 3 of our quadratic x squared minus 2x plus 3 and then dx. All right, so I take the antiderivative of that. That's going to give me x to the third, but then I've got to have the 1/3 out in front, minus x squared, and I would have 1/2 out in front, but I need it to be 2, so I'm going to leave that like that, plus 3x, and that is going to be evaluated from 0 to 3. All right, so now I plug in 3. 3 to the third is 27. 27 divided by 3 is 9. So that becomes 9 minus 3 squared is 9 plus 3 times 3 is 9. That's one part. And then minus, when I plug in 0, gives me 0. So this gives me exactly, those cancel, gives me exactly 9. Okay, so you can see I'm pretty close. Looks like I've over counted, but that would make sense if I'm adding up all these extra bits and there's only a little bit missing there. Makes total sense. All right. On to indefinite integrals. All right, indefinite integrals are when we are thinking of this as a function. We don't have values there. We're looking at it in more general terms. I have to decide which of these are going to be integrated by the appropriate technique. Hopefully, at least one or two of them are ones you can just do sort of straight up with a little bit of modification. This one looks like they're 2 separate parts, so I can break this down into the integral of the first part. And what I'm going to do is I'm going to divide this x into each of these to separate this. That's x to the 1/2. When I have 12 and then x to the 5th divided by x to the 1/2, I simply subtract the exponents. So this is 12, and then x to the 4.5 exponent. I can keep that as 9/2 if I want, or I could write it even as a decimal, but we're more used to doing it like this. And then plus 3, and then 2 minus 1/2 is 1.5, or 3/2 power, okay? And then plus e to the x, okay? And then dx. Well, I can do each of these individually, all right? Here using the reverse of my power rule. So I'm going to add 1 to that, and that's going to be x to the 11/2. So when I bring that out front, then I need that to equal 12. All right, so that's 2/11 times 12. So 12 times 2/11. All right, because when I bring that out front, that would I want to cancel and keep the 12. Plus, and then x is going to be, when I add 1 to this, that's going to be 5/2, and then that's going to be 3 times 2/5. And then this is just going to be e to the x. All right, and then don't forget our plus c. All right, so now I can clean this up. 12 times 2 is 24/11, x to the 11/2, plus this is going to be 6/5, x to the 5/2, plus e to the x plus c. All right. This guy down here, this looks like it's a complicated one because it's kind of got a product rule thing going on here. What you're looking for when you're doing integration by u substitution is that the part that's making it more complicated, when you take the derivative of that, you sort of see remnants of it over here, so we can combine it. And that is definitely this case, because when I take the derivative of x to the 1/2 power, I get 1/2 x to the minus 1/2 power, and that sends that square root into the denominator. So the derivative of this is definitely linked to that. So I'm going to go with u substitution. So I say let u equal radical x. Okay? And then when I take the derivative of both sides, I get du here. Well, radical x is, as I said, x to the 1/2. And when I take the derivative of this, I bring that 1/2 out front. I kick it down by subtracting 1, so that gives me minus 1/2, which gives me 1 over 2 square root of x. Okay? Don't forget the dx, because what I'm hoping to do is substitute out the dx and this, and you'll see that's exactly this part right here. All I need to do is multiply both sides by 2, and I get that. So 2 du is equal to 1 over radical x dx. That's the critical thing, because now I can substitute in and say it's the integral of the sine of u, and then you'll see du, because I can replace the dx and the 1 over radical x with, 2 du, but I'm going to bring that 2 out front. Okay, so that's why you want to check your work. Now I can do the integral of this. It's going to be 2. The derivative of the sine is the cosine. The derivative of the cosine is the minus sine. So I need to make it minus cosine. I'm going to put that in parentheses of u. And then plus c. Alright? I'm going to bring that minus outside and say it's minus 2 cosine of radical x then plus c. That's the answer. If you're not sure, take the derivative. All right, your check. And so I have sine of radical x times 1 over radical x, which is exactly what I started with, except it's just in a different order. But it's multiplication, so it does not matter. All right. This guy here is a bit of a challenge because we're not sure exactly how to do it. Integration by parts, and we're not sure what part to start off with. If we began with let u equal x, yes, when we take the derivative it does make it simpler on this side, but when we go to this side and let this be equal to dv, taking the integral of that does not make it simpler. So you might need to spend some time trying both ways. This is going to happen occasionally. It turns out that if we let u be equal to ln of x, when we then take the derivative of both sides, I'm going to get du is equal to 1 over x dx. All right? And then when I let dv be equal to x dx, okay, that's this part, then I can integrate and I get v is equal to 1/2 x squared. All right. If I then go to my formula for integration by parts, you'll remember it's uv minus the integral of v du. So when I fill in the parts, I'm going to have u times v is going to be 1/2 x squared ln of x, and then minus the integral of 1/2 x squared times 1 over x dx. All right, so I fill in this part and this part right there. So what does this become? Well, this becomes 1/2 x squared ln of x minus, well, this x cancels with that, and it's the integral of 1/2 of x dx. When I integrate this, I get 1/4 x squared, okay? And then I do plus c, all right? And you're done, but you want to check that, so I'll maybe leave it to you to check because I think I'm running out of time.